Hello and welcome to this tutorial. In this tutorial, we're going to be looking at quadratic inequality in one variable. By taking this tutorial, I'm assuming you're already used to the concept of inequality and also the concept of quadratic expression. So if you're not used to that, feel free to check any of our tutorials under quadratic equation and also inequality. So in this tutorial, we shall attempt to find the solution to the set of quadratic inequality of the form ax squared plus bx plus c greater than or equal to 0, or ax squared plus bx plus c less than or equal to 0. So from these two expressions, we can see this, which represents the general form of quadratic equation, and also the positive greater than or equal to or less than or equal to that represents inequality. So we shall be looking at three different methods that we can use to solve this form of equation. In the last tutorial, we looked at the first method of solving quadratic inequality in one variable, which is simply the analytical method. In this particular tutorial, we're going to be looking at the second method. So we look at the method 2 of solving quadratic inequality in one variable. So in this particular method, we are going to be looking at the parabola graph to solve quadratic inequality. So we're going to be using our knowledge from quadratic graph to solve quadratic inequality. So we should recall from quadratic equation that the general formula for quadratic expression is given as f of x equal to a squared plus bx plus c. So we have our general expression for quadratic expression, and we also know that the concept of the type of roots that a quadratic expression has, we have real and distinct roots, we have real and equal roots, and we have imaginary roots. So if you consider our quadratic expressions, we have real and distinct roots, we know that b squared minus 4ac must be greater than 0. So for us to have real and distinct roots, so meaning we are going to have two different roots, our alpha and beta, to form the root of this quadratic equation, given that b squared minus 4ac is greater than 0. So we are going to be using this fact to solve a quadratic inequality in one variable. So we know that the graph of a parabola crosses the x-axis at two distinct points, given that we have real and distinct roots. So this fact, as I mentioned, can be used to solve the inequality of the form ax squared plus bx plus c is greater than or equal to 0, or we have ax squared plus bx plus c is less than or equal to 0. So now let's look at the parabola graph, and now we can use this to solve quadratic inequality. So let's look at the first graph. So if I have my x-axis like this, and in this case, let me change this to another color. Okay. So if I have a graph of this form, so I know that I have a real and distinct root. So if a, which is the coefficient of x squared, is greater than 0, so I'm going to have my graph to be a cup-like structure. So if you recall from quadratic equation graph, so whenever we have our curve cutting the x-axis, and in this shape we have that the coefficient of x squared, which is a, must be greater than 0. So here we have this type of graph. So this is our x-axis, and we know that everything above x-axis is positive. So here we have the positive side, and here we have the negative side. So meaning that simply we have here that y is greater than 0, and here we have y is less than 0. So the same knowledge from quadratic graph, we know that if our curve cuts the x-axis at 2 points, so we are going to have this to be the first root and the other part to be the second root. So if I have our alpha 1 here, and this to be our beta 1, so you have the root of the equation to be alpha and beta. So if you know that alpha and beta are the zeros of the polynomial, so we can use this method to solve quadratic inequality. So for the intervals, if you look at the first graph that we have here, for the interval x less than Let me just put this down. So for the interval x less than alpha 1, so if you have x less than alpha 1, since we know this is our x-axis in yellow, so everything less than alpha 1 is towards this side, to the left hand side. Or if you have x greater than beta 1, so everything greater than beta 1 is towards the right hand side. So if we have this point, for example, which is x less than alpha 1, so if you have to find the value of y, we can only trace it up to meet this curve. The same thing if you are looking for the value of y whenever x is greater than beta 1. So for example, we have our x to be this point. We can't trace it down because it won't meet the curve. So we can only trace it up, and we know that everything above our x-axis is positive, meaning that it is greater than 0. So here we can say that for these two conditions, x less than alpha 1 and or we have x greater than beta 1, so we can have that a s squared plus bx plus c is greater than 0. So we know that f of x is f of x, this is also y is greater than 0. So for this condition, we are going to have ax squared plus bx plus c greater than 0. I've already explained this. So whenever we are going to find the value of for x, whenever x is less than alpha 1 or x is greater than beta 1, so the answer of y will always be positive, because the only point on the curve that any of these x can meet is towards the positive y-axis, which is x if you are going up above the x-axis. So noting this fact, so we simply have that the condition that satisfies this is alpha 1 less than x. Okay, let me clean this off. So again, if you look at the second condition, so the first one we looked at was having x to be less than alpha 1 and x to be greater than beta 1. So what if we look at the condition that falls in this range? So that is simply alpha 1 less than x less than beta 1. And whenever we have any points on the x-axis that falls in this range, we can't trace the point upward because it won't meet any point on the curve. So we can only trace it down, and it's going to meet the point A. And we know that everything below this is negative. So yeah, just like we have positive here, so we are going to have that ax squared plus bx plus c less than 0. So take note of these two conditions. If you have a parabola, so we look at everything to the right of b1 and everything to the left of x1. So here we have x less than alpha 1, everything to this point, as I mentioned, and also x greater than beta 1, everything to the right of beta 1. So if you take any value of x here, we can only trace it to meet the curve at the top side. So, and at the top side, we know that y is greater than 0, meaning that it is positive. Here we have greater than 0. And if you pick any point that falls in this particular range, so we can't trace it up, we can only trace it down. And whenever it meets any of these points, and we trace it to the corresponding y coordinate, here we are going to have negative y-axis. And then that's why we have y less than 0 here. We know that this is simply y or f of x. So that's the first graph that we looked at. So now the second case of parabola graph, which is quadratic equation graph, is when we have a, which is the coefficient of x squared, to be less than 0. So let's produce another graph. Again, if you have this graph, and if you have x squared, the coefficient of x squared to be less than 0, meaning that we have a to be less than 0. So we're going to have an n-like graph. Something of this nature. So if you have a graph of this form, again, we have these 2 points to be the root of this quadratic graph. So we can have this as alpha 2 and this to be beta 2. And here, as I mentioned, for this graph, we know that a is less than 0. So that's when we have the coefficient of x squared to be less than 0. So the same condition we looked at in the former graph, we are going to look at a. So since we have our straight line to be the x-axis, we know that to the top right side, we have this to be positive, and then we have y greater than 0, and downward, we have this to be negative y-axis, where we have y less than 0. So the same thing we are going to be looking at the condition we looked at in the former example. So whenever we have x less than, so let me put this down again, for the interval x less than alpha 2 or x greater than beta 2. So whenever we have x that falls to the left hand side of beta 2, meaning that we have our x in any of these points, or we have our x in any of these points. So we can't trace the value of the corresponding value of y to the top side, we can only trace it to the downside. And if it meets any of these points on the curve at the downside, we can only trace it to the negative y-axis, assuming this is the y. Assuming if you have the y-axis, so assuming you have this y-axis, so this is the positive y and this is the negative y. So you can only trace this to meet the negative y. So for this condition, so we know that our f of x must be less than 0. So we know that a x squared plus bx plus c must be less than 0. Also, if any of the points in x falls in this range, so we can't trace the corresponding value of y to the negative y-axis because it won't meet the graph, which is the curve at any point. So we can only trace it to meet the curve on the positive y-axis. And if it meets the curve here, so to get the corresponding value of y, we trace it to the positive y-axis. So if it meets y at this point, so we are going to have this to be positive. So for the range alpha 2 less than x less than beta 2, so we are going to have our expression a x squared plus bx plus c to be greater than 0. So we are going to be using these two analysis and these two facts to solve quadratic inequality in one variable. So let's look at the first example. First example, we are going to be solving the quadratic inequality given by x squared minus x minus 10 less than 2. So here we have x squared minus x minus 10 less than 2, and in this case we can simply rearrange to have x squared minus x minus 12 less than 0. So here we have x squared minus x minus 12 less than 0. So we have already know that this belongs to this particular condition. So we have to firstly analyze our question. So here we have a x squared plus bx plus c less than 0. So we know that here we have a to be greater than 0. So because the coefficient of x squared is greater than 0, and we know that the coefficient of x squared is a. So here we have a to be greater than 0. So the type of graph that we are going to have is the cup-like structure, which is in this form. So we know that for this particular expression, we have this type of graph. So the next thing we have to do is to find the root of this expression. So first we factorize, and how do we factorize this? We are going to have this to be x plus 3, x minus 4. So we have x equal to negative 3 and x equal to 4. So for this particular graph, I have my first root to be negative 3 and second root to be 4. So for me to have less than a, so I know that it falls to y less than 0. So I know that for y less than 0, I'm looking at the negative axis. So if I go back to the analysis I made in the first instance, so we know that if you have this kind of scenario, this type of graph, for us to have y less than 0, which is ax squared plus bx plus c less than 0, So this condition will be satisfied, which is alpha 1 less than x less than beta 1. And it's not complicated to also observe here that for us to have this expression less than 0, meaning that our range must fall in this particular point of the graph. So we know that whenever we have any x here, we can only trace it to this graph. We can only trace it to this point on the curve. And everything below the x-axis is less than 0. So here we know that this particular section of the graph satisfies our inequality. So we simply draw the answer to be -3 less than x less than 4 to be the solution to this quadratic inequality. So if that is clear, we can move to the second example. So let me just scroll so that we have more space to work with here. So the second example, let's look at another case where we have to solve a quadratic expression s squared minus 2x minus 3 greater than or equal to 0. And if you have greater than or equal to, or we have only greater than, we still treat them as the same condition. So the same thing, the first thing we have to do is to find the root of this quadratic expression. Here we have, to factorize this, we have x plus 1, x minus 3 greater than or equal to 0. So we have the root of this expression to be x equal to -1 or x equal to 3. So again, I draw out the parabola. So I have half this case, and also a is greater than 0. So meaning that I'm going to have a cup-like structure. So which is the structure A. But in this case, I'm looking at greater than 0, meaning that I'm looking at everything above the x-axis. So I know that everything above the x-axis can either fall in this side or in this side. So if this is my alpha 1, which is -1, and this is my beta, which is 3. So for me to have this particular expression to be greater than 0, meaning that my point must not fall in this, x must not fall in any of this side, it can only fall to the left of alpha 1 or to the right of beta 1. So I'm going to have all these points to satisfy my condition. And now can I draw this out? So this is going to be x less than -1, and this is x greater than 3. So joining this, I'm going to have the solution to the quadratic inequality is simply x less than -1. In this case, we have less than or equal to, or we have x greater than 3. And here we have the solution to the quadratic inequality. So this also corresponds to what we had while analyzing this. So let me just scroll down. Yes. So we know that from the analysis, for us to have greater than or equal to 0, so we must have s less than alpha 1 or s greater than beta 1. So the same case was applied in the example. And we have x less than 1, -1, or x greater than -3. So let's look at third example where we have a to be less than 0. So looking at the third example, if you are to determine the solution of the inequality 3 minus 5x minus 2x squared greater than 0. So in this case, we have the coefficient of x squared, which is -2, to be less than 0. Here we have a less than 0. So but the first thing we have to do is to find the root of this quadratic expression. So factorizing this, we are going to have 1 minus 2x, 3 plus x, 3 plus x greater than 0. And we have the roots of the expression to be x equal to 1 over 2 and x equal to -3. So again, I have to draw my parabola to represent this. And whenever we have x to be less than 0, we are going to have the n-like structure for my graph. So I know my graph looks like this. So for my graph to look like this, I have my alpha, which is -3 over here, and beta, which is 1 over 2. And if you look at the expression that we are given, we have that f of x is greater than 0. And for f of x to be greater than 0, meaning that we are looking at the top side of our graph, which is the point above the x-axis. So for us to have a point whereby it touches any point in this curve, so we can only have the point of x to be in this box, in this range here. So it can only be in this range. So if our x is to touch the positive y-axis, or if it's to touch the curve, so x can only be any value in this range. So, and for it to be in this range, so we can simply write out our solution to be -3 less than or equal to x. So we have -3 less than x less than 1 over 2. So we have -3 less than x less than 1 over 2. So if you look at the analysis that we made during the illustration, you see that it tallies with this. So the last example on this, to show the last case that we can have. So if you have to find the solution to the inequality, 8 plus 10x minus 3x squared less than or equal to 0. So in this case also, we have a to be less than 0, which is the coefficient of x squared, in this case -3. So the first thing we have to do also is to find the root of this quadratic expression by firstly factorizing it. And if you factorize this, we are going to have 4 minus x and 2 plus 3x. So the roots of the equations are x equal to 4 and x equal to -2 over 3. So again, I have my parabola, and since a is less than 0, which is the coefficient of x squared, I'm going to have an n-like structure for my graph. But in this case, we have less than 0. So for us to have less than 0, we are looking at the downward part of the graph, which is anything below the x-axis. And we know that for us to have a point in x that will touch the graph, or simply that we touch the curve below the x-axis, it can be at this point. If it's at this point, it won't touch the curve. So it can only be to the left of alpha, our alpha in this case, which is -2 over 3, and beta to be 4. So it can either be to the left of alpha or to the right of beta, which is simply to this point and also to this point. So we can just simply demarcate this using strokes. And this shows the area that satisfies the inequality. So we can simply write this to be x less than -2 over 3, or we have x greater than 4 to be the solution to this quadratic inequality. So that's simply how we can solve quadratic inequality using parabola method. So here simply this is going to have less than or equal to, this is going to have greater than or equal to. So thank you very much for joining me in this tutorial. If you like it, don't forget to like, share and subscribe to this channel. And if you have any question, feel free to drop it in the comment section below and I will reply to you as soon as possible. Thank you, and I will see you in the next tutorial.